Alright, this is equation 6 through 8. So starting off from last time, we found that the power incident is equal to the solar radiation density, or I of O, times width times length, or the area of the window, times the sine of theta and beta, or the distance between the ground, or the angle between the ground and the sun, and the angle between the oven and the ground. Now, in equation 6, we are introduced to tau, which is the fraction of light that passes through the window. So, for example, something like a piece of glass would have a higher fraction of light that passes through the window than a piece of paper, for example. Now, tau is used as P transmitted is equal to the power incident times tau. So this equation up here is equal to the power transmitted as long as it is multiplied by tau. Now in equation 7, we are given A, or the absorption coefficient. So a black shirt or black leather seats in a car are obviously going to absorb a lot more heat than a reflective surface like white would. So we are given the equation power absorbed is equal to the power transmitted times the absorption coefficient, or A. Now this is all put together in equation 8. So we end up with P absorbed equals I of O times the area of the window times tau times the absorption coefficient times sine of theta and beta. Alright, this is equations 9 through 11. So in equation 9, we are given that P out is equal to U times A times TIO minus T ambient. So U here would be the overall heat transfer, A would be the area in which heat flows, and then T would be the temperature in Celsius. So TIO would be the temperature inside of the oven, and then T ambient would be wherever the heat is transferring to. Now we are given a better look at this equation as it gets more specific. In the equation, P out equals U of SB times A of SB, which is multiplied by the temperature inside the oven minus the temperature that is lost to the outside, or ambient, plus UW times A of W, which is then multiplied by the T of IO minus the T of ambient. Now, why this is split up this way is because the window and the sides and base of our oven are most likely going to be made out of different materials. And so we have to account for the different heat transfers and the areas of these different materials are between the base and the window, as the window's area is probably a lot smaller than the area of the sides and base. Now this is just simplified in equation 11 to one equation, or one easy line. P out is equal to the heat transfer of the sides and base times the area of the sides and base plus the heat transfer of the window times the area of the window, which is then all multiplied by the temperature inside the oven minus the temperature ambient.
Equation 12 basically calculates the amount of energy leaving the oven. You do this by grabbing or dividing the thickness of the first material by the coefficient of thermal conductivity from the first material. And for every material you have, you keep on adding it. So if I had two materials, I would divide the first material's thickness uh, by its thermal conductivity, and then I will add that to the thickness of the second material uh, divided by the coefficient of thermal conductivity. And basically, the more materials you have, um, the it will reduce the overall heat transfer. Equation 13 is like what are variables given to us, which affects the energy of the inside the solar oven. So an example would be like the area that where the or the angle or the sun rays enter the solar oven, and so we're basically looking for the internal temperature of the oven, and so like this is like after it reaches a thermal equilibrium, and so algebraically looking for T in your equation, you'll get T equals. Wait, you get this equation.
Okay, so for equation 15, the overall heat transfer coefficient is equal to A times the temperature inside the oven squared plus B times the temperature inside the oven plus C. And we could tell this is a quadratic equation. And we're giving a data table over the temperature inside the oven, which we could like plug in the values here. We could put some random dots. And using this equation, we're going to try to solve the graph, or at least try to get the equation for it, which is called the curve fit, which when we plug in our values in for A, B, and C, we're able to find out the equation, just like how we would normally do in a quadratic equation. You know, you're just substituting in values to try to find A, B, and C. Okay, so for equation 16, it's the exact same as equation 14, except for the fact that our overall heat transfer coefficient for the window, which is UW, is now switched out for our old equation for equation 15, which is A times the temperature inside the oven squared plus B times the temperature inside the oven plus C, which is now over here as we figure out from equation 15. And that's about it. Okay, so for equation 17, it's the exact same as equation 16, except for the fact that instead of searching for the temperature inside the oven, now we're subtracting that as well as subtracting our other big equations to try to equal out to 0. So same thing as equation 15, how we weren't really given the factors in for our equation, but we could substitute and try to find like the curve fit. We're doing the same thing here. We're plugging in different values, especially for like the temperature of the oven, until we get to 0, or at least as close as we can to 0.